Hello. Today I'd like to conclude our discussion of moles by looking at moles and their relationship to chemical reactions or chemical equations. This concept is more commonly referred to as stoichiometry calculations or mole calculations involving chemical reactions. Let's take a moment and understand what a balanced chemical equation really tells us. If we look at the equation 2Ag solid plus S solid yields Ag2S, in other words, silver solid plus sulfur solid produces solid silver sulfide, we can learn a lot about the necessary ingredients, so to speak, that must come together to make this reaction happen. On an atomic scale, the reaction tells us that 2 atoms of silver must react with 1 atom of sulfur to produce 1 formula unit of silver sulfide. On a much larger level, in other words, on the molar or mole level, it tells us that 2 moles of silver are necessary to react with 1 mole of sulfur in order to produce 1 mole of silver sulfide. Or if you care to think about moles in terms of number of atoms, as opposed to 1 mole, 2 mole, etc., then what we're really talking about is 2 times 6.02 times 10 to the 23rd silver atoms reacting with 1 times 6.02 times 10 to the 23rd sulfur atoms to produce 1 times 6.02 times 10 to the 23rd silver sulfide formula units. The take-home message here is that the equation, the balanced equation, contains coefficients, and that those coefficients are not ratios of grams, but rather ratios of moles. So if we wish to use a balanced chemical equation in our calculations, before it's useful, we must be working in quantities of moles, not in grams. We can convert from moles of one substance to moles of another, provided we have the balanced equation. An example on your screen is iron solid reacting with solid sulfur to produce iron 3 sulfide. In this case, 2 iron must react with 3 sulfur to get 1 iron 3 sulfide. Based on this reaction, which contains 2 reactants and 1 product, we can generate the 6 mole-to-mole conversion factors you see on your screen. These 6 conversion factors allow us to convert from moles of one substance to moles of another. For example, we can now answer the question, given the above balanced equation, how many moles of sulfur are needed to react with 4.5 moles of iron? We look at the ratio of moles of sulfur to moles of iron in the above equation, and we note that 3 moles of sulfur are required to react with 2 moles of iron. Using that ratio, it is possible to convert from 4.5 moles of iron to 6.8 moles of sulfur. This is accomplished by multiplying 4.5 moles of iron by 3 moles of sulfur and then dividing by 2 moles of iron. You notice moles of iron cancel, and we find out how many moles of sulfur that we need in order to make this reaction run to completion. However, everyone knows that we don't readily, in the lab, work with moles. Instead, we have balances that measure the amount of grams. How then do we get from grams of a substance to moles, and from moles of one substance to moles of the other, and then finally back to grams? For example, how can we truly calculate the grams of water that are produced when 15 grams of hydrogen gas react with excess oxygen gas? The balanced equation for the reaction is that 2 moles of hydrogen gas must react with 1 mole of oxygen gas to produce 2 moles of water. The plan for solving this problem involves several steps. Number 1, we must calculate the molar mass of hydrogen gas. Number 2, we must convert grams of hydrogen to moles of hydrogen utilizing the molar mass. Number 3, we must convert moles of hydrogen gas to moles of water using that mole-to-mole ratio from the balanced equation. This is the new step in this process. We already knew how to calculate the molar mass. We already knew how to convert from grams to moles. The new step is inserting this mole-to-mole ratio, where appropriate, from the balanced equation. Once we've changed from moles of hydrogen gas to moles of water, it is necessary to calculate the molar mass of water, and then finally, in step 5, to utilize that molar mass to convert from moles of water to grams of water. Now, it is possible to carry out this calculation in a single long calculation that involves 5 conversions. Or you can carry out the calculation in 5 individual steps. I'm going to show you the solution to this problem both ways. You'll note that regardless of which way we do it, we end up with the same answer. Let's first look at the solution to this problem, solving each step individually. You'll note in step 1 we calculate the molar mass of hydrogen, by taking 2 times 1.01, which is the molar mass or approximate molar mass of hydrogen. In this case, we get a molar mass of 2.02 grams per mole. Note, when calculating the molar mass of the hydrogen gas, we have ignored the coefficient that appears in front of hydrogen gas in the equation. It is not part of our molar mass calculation. In step 2, we're going to utilize that molar mass to calculate moles of H2. As per usual, we're going to take our 15 grams of hydrogen gas and divide it by the molar mass of hydrogen gas, which is 2.02 grams per mole. In other words, 15 grams of hydrogen gas is the same as 7.43 moles of hydrogen gas. We're now going to convert moles of hydrogen gas to moles of water vapor. In this case, we look at the balanced equation and note that the mole-to-mole ratio between water and hydrogen gas is 2 moles of water per 2 moles of hydrogen gas. In other words, 7.43 moles of hydrogen gas reacting with excess oxygen produces 7.43 moles of water vapor. Next, we need to calculate the molar mass of water, which is 18.02 grams per mole. We get this by taking 2 times the molar mass of hydrogen plus the molar mass of oxygen. Finally, we must convert moles of water to grams of water. As usual, to convert from moles to grams, we will multiply by the molar mass. 7.43 moles times 18.02 grams per mole gives us 134 grams of water that is produced from the reaction of 15 grams of hydrogen gas with excess oxygen gas. Just like we did on the previous example, just like we did previously, we can take this entire 5-step process and simplify it or combine it into 3 easy steps. The first step is to calculate the molar mass of hydrogen. The second step is to calculate the molar mass of water. And the third step is to utilize those two things along with the given information in the problem to reach the solution. In this case, we have combined the remaining 3 steps of that 5-step process just illustrated into one calculation. You'll note in this singular calculation we begin, again, by dividing by the molar mass of hydrogen. We then multiply by the mole-to-mole ratio from the balanced equation, which converts from moles of hydrogen to moles of water. And we conclude by multiplying by the molar mass of water. You will note, regardless of whether we did the 5 steps individually or whether we combined them together, we ended up with the same answer, that when reacting 15 grams of hydrogen gas with excess oxygen gas, you produce 134 grams of water. Now, the production of 134 grams of water from 15 grams of hydrogen gas and excess oxygen gas makes one very important assumption. That assumption is that the reaction is 100% efficient. In other words, this is the theoretical yield. In theory, if we react 15 grams of hydrogen gas with excess oxygen gas, we should get 134 grams of water. However, there is no reaction known to man that is 100% efficient. In other words, in the laboratory, we're actually going to obtain some smaller percentage of that 134 grams. There are many reasons why you cannot have a reaction that is 100% efficient. Those are not the focus of our present discussion. The focus of our present discussion is how to utilize the information provided to determine the percent yield of a particular reaction. In the case of hydrogen gas reacting with oxygen gas to produce water, we just realized or just calculated that if we start with 15 grams of hydrogen gas, our theoretical yield is 134 grams of water, assuming, of course, we have an unlimited or excess supply of oxygen. Let's pretend that we ran this experiment in the lab, and instead of obtaining 134 grams, we actually obtained 125 grams. Knowing what we actually obtained, we can calculate the percent yield. You take the actual divided by the theoretical yield times 100%. In this case, 125 divided by 134 times 100 is 93.3% yield. It is not 100% efficient, but this reaction is relatively efficient. It's worth noting here that the actual yield must be given. It is not a number that you can come up with out of thin air. The only way to calculate the actual yield is if you know both the percent and the theoretical yield. But typically, in a real setting, the actual yield is measured in a lab and then provided for the calculation. Now, up until this moment, we have been looking at chemical reactions that involve solids, liquids, gases, and some aqueous solutions. We have only measured the amount of any of these substances in grams. It's not, however, very efficient to measure the mass of a solution. And the reason that it's not efficient in terms of a chemical reaction to do that is because the solution contains water, which oftentimes does not react, and the solute, which does react. It turns out that there is a better way to measure the amount of solute in a solution and utilize that information in chemical reactions. That better means for measuring the amount of solute is known as molarity, which is abbreviated with a capital M. Again, molarity is not the focus of this discussion. Its use with chemical reactions, however, is. Molarity is the moles of solute divided by the liters of solution. If you rearrange the molarity of equation, you can solve for the moles of solute. In other words, the moles of solute is the molarity of the solution, or its concentration, times its volume in liters. If you know both the molarity and volume of a solution that you are utilizing, you can calculate how many moles of solute are in that solution, and then you can use that information in conjunction with balanced equations to solve problems like we were just looking at with grams. Perhaps an example will best illustrate this process. Let's attempt to answer this question. If 32.6 milliliters of 0.185 molar NaOH solution is needed to neutralize 25 milliliters of HCl, what is the molarity of the HCl solution? We're given a balanced equation that says NaOH plus HCl yields NaCl plus H2O. In other words, the mole-to-mole ratio between NaOH and HCl is 1:1. To solve this problem, we're first going to need to convert the volume of the NaOH solution, 32.6 milliliters, to liters. 32.6 milliliters is 0.326 liters. If we multiply that by the molarity, which is 0.185 moles per liter, you'll note that the liters cancel, and we are able to calculate that there are 6.03 times 10 to the minus 3, or 0.00603 moles of NaOH present in this solution. Knowing the moles of NaOH, we can use the mole-to-mole ratio from the balanced equation to calculate the moles of HCl. In this case, the mole-to-mole ratio is 1 mole of HCl per 1 mole of NaOH. Note if you multiply by this mole-to-mole ratio, the moles of NaOH cancel, and we end up with 0.00603 moles of HCl. If we want to calculate the molarity of HCl, we must take the moles of HCl divided by the total volume of HCl in liters. We are aware from the problem that we started with 25 milliliters of HCl, and 25 milliliters of HCl is 0.0250 liters. If we take 0.00603 moles of HCl divided by 0.0250 liters, we calculate that the molarity of the HCl solution in question is 0.241 molar. There are a wide variety of calculations related to stoichiometry that involve molarity. Your textbook will illustrate a few of those other varieties in its discussions of solutions. If you have further questions about solutions and chemical reactions, you are urged to consult either your instructor or the book, or both. Let's continue our discussion now by adding one final element to the stoichiometry calculations we have been discussing. And this is the idea of limiting reagent. You might notice in all of the examples we have discussed so far that we have really only talked about the amount of one reagent, even if the equation had two reagents present. One of them was always present in excess. What if we didn't know which reagent was present in excess? Could we figure it out? How would that change our calculation approach? To understand this idea, let's start with a non-chemistry example. Let's assume we want to make a turkey and cheese sandwich. Let's assume that the sandwich contains 2 pieces of bread, 2 pieces of turkey, and 1 slice of cheese. In other words, 2 turkey plus 1 cheese plus 2 bread equals 1 sandwich. The question: if we have 6 pieces of bread, 8 pieces of cheese, and 4 pieces of turkey, how many sandwiches can we make? Well, the 6 pieces of bread will allow us to make 3 sandwiches. The 8 pieces of cheese would allow us to make 8 sandwiches. And the 4 pieces of bread would allow us to make 2 sandwiches. If we assume we can only produce complete sandwiches, then we can only produce a maximum of 2. Because after we produce those 2 sandwiches, we have run out of bread. The calculations you just carried out briefly in your head are illustrated on the screen. It took you all of 30 seconds to come up with the correct answer. In this example, bread is the limiting reactant. In other words, it's the substance that we run out of that stops this process from moving forward. The amount of sandwiches produced by the limiting reactant is 2, which is the theoretical yield of this particular process. Let's look at a similar example through a chemistry lens. Before we do that, however, it is important that we understand when are we facing a limiting reactant problem and must we go through these steps, and when aren't we. If you come across a problem where you know the number of moles, or conversely, the number of grams of more than one reactant, you must assume that you may be in a limiting reactant scenario and therefore follow these steps. Number 1, you must determine the moles of each reactant. Number 2, you must calculate moles of the desired product starting with each reactant, and from that you will get a couple of pieces of information. The reactant that produces the fewest number of moles of the desired product is known as the limiting reactant, and all other reactants are present in excess. That smaller number of moles of the desired product is the actual amount produced. In other words, the theoretical yield of the process. And at that point, if it is necessary, you should convert the number of moles to grams. Let's look at an example and go through this process. The question: how many grams of aluminum chloride, which has a molar mass of 133.33 grams per mole, are produced when 20 grams of aluminum, molar mass 26.98 grams per mole, reacts with 20 grams of chlorine gas, molar mass 70.90 grams per mole? The balanced equation for this process is 2Al plus 3Cl2 gives us 2AlCl3. In this process, we are going to calculate the mass of aluminum chloride produced beginning with each reactant. If we begin with the 20 grams of Al and divide by its molar mass, 26.98 grams per mole, multiply by the mole-to-mole ratio between aluminum chloride and aluminum, which is 2 moles of aluminum chloride over 2 moles of aluminum, and finally multiply by the molar mass of aluminum chloride, which is 133.33 grams per mole, you will notice that from 20 grams of aluminum, one can theoretically produce 98.8 grams of aluminum chloride. If you repeat the calculation beginning this time with 20 grams of chlorine gas, you will note that instead of producing 98.8 grams of aluminum chloride, you now produce 25.1 grams of aluminum chloride. This tells me that chlorine gas is the limiting reagent and that the theoretical yield of this process is 25.1 grams of aluminum chloride. Okay? If you were to run this process in the lab, it is possible that you would be able to determine the actual yield and then the percent yield for this reaction. We won't carry the calculation that far for this particular process, but it is worth noting that it's possible to do. Limiting reagent problems do not present any new material to chemists. They simply require us to perform more calculations, one calculation beginning with the starting amount of each reactant, in order to determine what the yield, or the theoretical yield of the reaction is. It is strongly encouraged that you practice many limiting reactant problems in the coming days and weeks in preparation for upcoming exams and quizzes. If you can carry out these calculations, you have a good understanding of the mole concept when it relates to chemical reactions. Again, your instructor is available, as well as your textbook, to provide additional guidance.